Okay, in today's lecture, we're going to start our Chapter 11 material on differential calculus. And this is really the first part of the course where we'll jump into calculus itself rather than just a pre-calculus review. So in this first section, 11.1, we're going to talk about limits. And limits are really the building blocks for all of calculus. So as we move through the course, we'll see that other major topics which we're going to talk about, for instance, derivatives or integrals, are actually all defined in terms of limits. So limits are really the true building block of calculus. So let's try to introduce the idea by considering an example. So let's consider the function f, which is defined as f of x is equal to x squared minus 1 over x minus 1. Now this function is undefined at x equals to 1, and we ask the question why. Well, 1 is not in the domain of this function. Here we have a rational function, that is a quotient of two polynomials, where our denominator is equal to x minus 1, so at x equals to 1, we would have a denominator of 0. And we know that division by 0 is undefined, so we would have a function which is undefined at the value x equals 1. However, for this function, it is defined everywhere else. So for every other value of x not equal to 1, this function is defined. So we could consider values of this function, f of x, by taking x very close to 1, but not equal to 1. So let's see what happens when we do this. If we evaluate f of x for values of x that are very close to 1, let's see what we have. So starting with a value of 0.9, if you evaluate this function at x equals 0.9, either by using a calculator or some algebraic simplification, we see that the value of f of x is 1.9. Now if we move a little closer to 1, let's say we take a value of 0.99, evaluating our function, we get a value of 1.99. And then moving even closer to 1, we would have 0.999, getting very close to x equals 1 now, and the value of our function at that point is 1.999. And then at x equals to 1, it's undefined. Now let's see what happens if we're approaching 1, say by using values of x that are a little bit larger than 1, maybe starting with 1.1, so a number greater than 1 but pretty close to 1. If we evaluate our function at that point, we have a value of 2.1. And as we start moving closer to x equals 1, let's say we take x equals to 1.01 or 1.001, and we evaluate our function at those values, we would have 2.01 or 2.001. So we can ask ourselves then, well, what do the values of the function seem to be approaching as our values of x are getting very, very close to 1, but not equal to 1? So here, when we're moving towards the value of 1, by taking values that are slightly less than 1, or as we're moving towards 1 by choosing values of x that are slightly greater than 1, we see that the values of our function were 1.9, 1.99, 1.999, and as we were taking values of x a little bit greater than 1, and we were closing in on 1, the values of our function were 2.1, 2.01, and 2.001. So we're seeing that the values of our function seem to be getting close to the number 2. Now, when x is actually equal to 1, our function is undefined. It doesn't have a value at x equals to 1. However, the values of our function seem to be getting very, very close to 2 whenever x is being made very close to 1. So this is the concept of a limit. We would say, as the values of x are approaching the number 1, the values of our function f of x are approaching the number 2. So in this case, we would say that the limit of our function f of x as x approaches 1 is equal to 2. And mathematically, this has a special notation, so this would be denoted in the following way. So we have an LIM for limit, and underneath that LIM, we have x with a little arrow moving towards 1. So we would say x is approaching 1, and the function that we were considering in this example was the function x squared minus 1 over x minus 1. So we write out the definition of our function, and then it's equal to, in this case, 2, whatever number the values of our function seem to be getting closer to. So this first example illustrates the idea of a limit, is what's happening to a function as we make the values of x very, very close to some number, but not equal to that number. And it also illustrates how we could find a limit. We could find a limit by taking values of x that are very close to the number of interest and seeing what the corresponding values for our function f of x are doing. Now, another way that we can evaluate limits is graphically. If we're either given the graph of a function or we know what the graph of our function looks like, we can use those graphs to evaluate limits as well, maybe without needing to use a calculator. So in this example, I mentioned that this limit can also be found by looking at the graph of f of x. So for this example, the graph of f of x looks something like the following. So we have our xy axes, and the graph of this function is actually a line of slope 1 and y-intercept positive 1. However, it's undefined when x equals 1. There's a hole in the graph of our line at x equals 1 because our function was undefined there. So for every other value of x, it looks just like a straight line, but there's a hole in the line at that value where our function is undefined. So how can we use a graph to determine the value of a limit? Well, if we're interested in what's happening to our function as x is approaching 1, well, let's consider looking at our function, the graph of our function. So as the values of x, that is along the x-axis, as we're moving closer to the value 1, let's see what's happening with the values of our function. So moving along our line in the same direction as we're approaching 1, we see our line is moving towards this point where we have a hole. And if we approach the value 1 from the other side, let's say taking values of x that are a little greater than 1, and we move along our line in the same direction, we see the values of our function are approaching this hole. And in this example, the corresponding y value that we have here is the number 2. So looking at this graph, we could have also said the limit as x approaches 1 of this function f of x is equal to 2 by examining the graph. So that gives us a couple of ways that we could evaluate limits of functions, either by using a calculator to plug in numbers for x that are close to the desired number, or by examining our graph. So now that we've come up with kind of an intuitive idea for limits, let's look at a more formal definition. So more formally, we would say if f is some function, and we have a and capital L as some real numbers, we would say the following. If the values of the function f of x can be made arbitrarily close to the number L, that is, as close as we want to the number L, by taking values of x sufficiently close but not equal to the number a, then we say the limit of f of x as x approaches a is equal to L. And again, this is written as LIM for limit, with a subscript of x approaching a of the function f of x is equal to L. Okay. So the idea of a limit is if you can make the values of your function as close as you want to some number by taking the values of x sufficiently close to some number a, we would say the limit of that function is equal to the number L. Okay. So let's look at some other examples evaluating limits using the graph of a function. So in this first one, we have the graph of a function shown here in red, and we are asked in part A to find the limit of that function f of x as x is approaching 0. So on our x-axis, the horizontal axis, we're going to ask ourselves, well, what's happening with the values of my function as the x values are getting closer and closer to 0? So looking at the graph of our function as we follow along, we can see that our curve, as we close in on 0, is increasing, and it looks like as we're getting really, really close to 0 along the horizontal axis, the values of our function along the vertical axis seem to be closing in on the number 1. We can see that if we're following the graph of our function from the other direction. As we're getting very, very close to 0 on the x-axis, on the y-axis, the values of our function are getting closer and closer to this number, it looks like 1. So we would say that the limit as x approaches 0 of this function, f of x, is equal to 1. So let's look at some other examples. In part B, we have a different graph of a function, and we're asked for the limit as first, x approaches 0. So first off, as x is closing in on 0, if we look at the corresponding values for our function, we see that our curve, or our y values for this function, seem to be approaching the number shown here. So it looks like it's right in the middle of 2 and 4 on the vertical axis, so a value of 3 for this limit as x is approaching 0. Now let's look at another one. Let's say what happens to the function as x approaches 1. So looking on our horizontal axis, as the values of x are closing in on 1, we see that the values of our function seem to be closing in on a y value of 2. So the limit of our function f of x as x approaches 1 is equal to 2. And in the last part, we're asked about the limit of a function as x approaches negative 1. So here, as x is approaching -1 on the horizontal axis, by looking at the curve, the y values for our function seem to be closing in also on the value 2. So in this example, we're again illustrating how we can use the graph of a function to find information about the limit of a function. Okay. Now, in most of the examples that we'll consider, if we don't have the use of a graphing calculator, or if we don't have a calculator, say, to plug in values of x to our function, then we can't evaluate the limit by the means that we've discussed already. So in this next part of the section, we'll introduce some properties of limits, which will allow us to evaluate limits of functions algebraically without having to rely on a calculator. So this next theorem highlights some of the properties of limits, and let's take a look at them here. So here we will suppose that c is a constant, and f and g are two functions such that the limit as x approaches a of the function f is equal to capital A, and the limit as x approaches a of the function g is equal to b. So the following properties for limits hold. The first one is called the constant property. It says that the limit as x approaches a of any constant function is equal to that constant c. So if we're thinking about the value of a function, which is always c, regardless of what value of x we're approaching, our y value for that function is always the constant c. So we would say the limit of that constant function is constant. Now the second property is called the identity property, and it says that the limit as x approaches a of x is equal to a. And that kind of makes sense if we think about what a limit is describing. We're asking here, well, what happens to the values of x as x is getting closer and closer to a? Well, the values are getting closer and closer to a. So the limit of x is a if x is approaching a. Now the next property is called the sum difference property, which says that the limit as x approaches a of the sum or difference of f of x and g of x is equal to the sum or difference of a and b, the limits of the function. So really what this, we can think about this property in two parts. First, the sum property says, well, if I have the limit of a function f is a, and the limit of a function g is equal to b, as we're approaching some number, then the limit of the sum f of x plus g of x would be the sum of the limits, a plus b. And equivalently, the difference property says, well, if we were taking the limit of the difference, f of x minus g of x, the limit would be capital A minus capital B. That is, the limit of a difference of functions is equal to the difference of the limits. Now the next property is called the product property, which says the limit as x approaches a of f of x times g of x is equal to a times b. That is, the limit of a product of two functions is equal to the product of the limits of those functions. Number 5 is the quotient property, which says that the limit as x approaches a of f of x divided by g of x is equal to the quotient of the limits. A over b as long as the limit of our denominator, g of x, is not equal to 0. So the quotient property says the limit of a quotient is equal to the quotient of the limits as long as the limit of our denominator is non-zero. And the last property, property 6, is called the power property, which says that the limit as x approaches a of f of x raised to some power n is equal to capital A to the nth power. So that is the limit of a function being raised to a power is the same as first taking the limit of the function, so we get capital A, and then raising it to the nth power. So let's look at making use of these properties for some examples. So in this next problem, we're told to suppose that the limit of a function f of x as x approaches a is equal to 25, and the limit of g of x as x approaches a is equal to 10. And then we're asked to find the value of these indicated limits. So in part A, we are asked for the limit of g of x times f of x. So using the product property, we know that this is equal to the product of the limits. That is the product of the limit of g of x and the limit of f of x. But we were given those values in the problem statement. We were told the limit of g of x is 10, and the limit of f of x is 25. So the product would give us a limit of 250. All right. Now in part B, we have the limit as x approaches a of 3 times f of x. So here we're taking again the limit of a product of two functions, 3 and f of x. So using the product property, we know that the limit of this product is the same as the product of the limits as x approaches a of 3 and the limit as x approaches a of f of x. Now for this first limit, the limit as x approaches a of 3, we can use our constant property. Remember, property 1 says the limit as x approaches a of any constant c is equal to c. So in this case, the limiting value of 3 is equal to 3. And then we're multiplying by the limit as x approaches a of f of x, which in the problem statement we were told is equal to 25. So we have 3 times 25, or 75. Now in part C, we have the limit as x approaches a of g of x to the third power. So using the power property, we know this is the same as first taking the limit as x approaches a of g of x and then cubing the whole thing. But in our problem statement, we were told the limit of g of x as x approaches a is equal to 10. So here we have 10 to the third power, which is 1,000. And then in part D, we'll combine a few of our different properties. We have the limit as x approaches a of 5g of x plus 2 divided by 1 minus f of x. So we're taking the limit of a quotient here. So using the quotient property, this is the same as taking the limit of the numerator, that is 5g of x plus 2, and dividing by the limit of our denominator, which was 1 minus f of x. Now in the numerator, we have the limit of a sum, which is the same as the sum of the limits. I could first take the limit as x approaches a of 5g of x, and then I would add the limit as x approaches a of the constant 2. And that whole thing is divided by the limit of a difference in the denominator. So using the difference property, I can say this is the same as the limit as x approaches a of 1 minus the limit as x approaches a of f of x. So now in my numerator for this first term, I have the limit of a product, 5 times g of x, which is the same as the product of the limits. So we would have the limit as x approaches a of 5 times the limit as x approaches a of g of x plus the limit as x approaches a of 2, and the whole thing is being divided by the limit as x approaches a of 1 minus the limit as x approaches a of f of x. So let's see what we're left with here. In our numerator, the first term is the limit of a constant, 5. So using the constant property, we know the limit of any constant is equal to that constant, in this case 5, times we had the limit as x approaches a of g of x, which in the statement of our problem, we're told is 10. Then we're adding, we have the limit of a constant 2. So again, using the constant property, that limit is equal to whatever the constant is, in this case 2. And then we're dividing by, in our denominator, we have the limit of a constant 1, which is equal to 1 by the constant property. And then we're subtracting the limit as x approaches a of f of x, which in the problem statement we were told is 25. So simplifying, in our numerator, we have 50 plus 2, or 52, divided by 1 minus 25 would give us a negative 24. And so, of course, we could simplify this a little bit. We would have, this is the same as negative 26 over 12, which is the same as negative 13 over 6. So using these limit properties, we can evaluate, or if we know the limit of two functions, let's say f and g, we can evaluate the limits of other functions which are similar, or which involve those f and g functions. So let's look at some other examples. In this next one, we're asked to find the given limit, and in part A, we have the limit as x approaches 2 of a polynomial, 2x cubed minus 5x squared plus 8. So a polynomial is just a sum or difference of a bunch of individual terms. So by making use of the sum or difference rule, this limit is equal to the limit as x approaches 2 of 2 times x cubed minus the limit as x approaches 2 of 5x squared plus the limit as x approaches 2 of the constant 8. So I'm making use of the sum and difference property there to take my limit term by term. Now for these first two terms, we are taking the limit of a product, a constant times some power of x. So using the product property for limits, that first term is the same as the product of the limit as x approaches 2 of 2 and the limit as x approaches 2 of x cubed. Now for the second term, we had the limit as x approaches 2 of 5 times x squared, which is the same as the limit as x approaches 2 of 5 and the limit as x approaches 2 of x squared. And then our last term, we have the limit as x approaches 2 of the constant 8. So we're getting a little closer to evaluating this limit. Now looking at our first term, we have the limit of a constant, 2, as x is approaching 2. So we know by using the constant property, the limit of any constant function is just equal to that constant, in this case 2. Now for our second term here, the limit as x approaches 2 of x cubed, well, we're taking a power of x here, so using the power property of limits, we could say this is the same as limit as x approaches 2 of x quantity cubed. And then we're subtracting, well, again, my first term is the limit of a constant, 5. So the constant property says that that limiting value is equal to 5. And then we're multiplying by the limit of x squared, which is the same as taking the limit as x approaches 2 of x and then squaring it. Plus, our last term on the end is the limit as x approaches 2 of a constant, 8. So again, using the constant property, we just have a value of 8 there. So we're almost done. Here we have 2 times, looking at this term, we have the limit of x as x approaches 2, which is equal to 2. That is the identity property for limits. If we're taking the limit of x as x approaches 2, well, we have a value of 2, which is then being cubed. Then we're subtracting, we had our constant 5 times the limit of x as x approaches 2 is again 2 using the identity property, and that's then being squared. And then plus 8. So let's see what we're left with here. We have 2 times 2 cubed is 8, minus 5 times 2 squared is 4, plus 8. So here we would have 16 minus 20 is negative 4, plus 8 leaves us with a positive 4. All right. Now, something to notice here, by using these limit properties, we were able to split up our limit and eventually get it down to terms involving the limit of a constant or the limit of just x itself. Now, we could use these same sort of properties on any polynomial function, not just the specific polynomial that we were given in this example. And let's see what happens here. Eventually, to find this limit, we got it down into the following form. 2 times 2 cubed minus 5 times 2 squared plus 8. Now notice that that's exactly what we would get if we were to just take this function that we were given and plug in the limiting value of x, in this case 2. So here we were just plugging 2 into the value of our function, and that gave us our limiting value of 4. So here, since we could do those, or make use of those same properties for any polynomial function, we arrive at the following result. So looking at our theorem below, here we have a result for the limit of a polynomial function, which says if f is a polynomial function and a is some real number, then the limit as x approaches a of that polynomial is equal to f of a. That is the value of our polynomial at x equals a. So what the first part of this theorem says is for polynomials, we can easily evaluate the limit by simply plugging in the value of x that we're given. So we no longer have to make use of these limit rules in order to evaluate the limit of a polynomial as we did in part A. We know from here on out we could simply plug in the value of x that we're given. So let's take a look at our example in part B. We have the limit as x approaches 2 of the following rational function, a quotient of 2 polynomials. Now, using the quotient property of limits, we know that the limit of a quotient is equal to the quotient of the limits. That is the limit of our numerator divided by the limit of our denominator. And that's true as long as the limit of our denominator is non-zero. So let's make sure that we don't have a 0 for our denominator. Now what we're left with, since this was a rational function, a quotient of 2 polynomials, after we make use of the quotient property, the numerator and denominator are both limits of polynomial functions. And from our work in part A, what we just said, to evaluate the limit of any polynomial, you can simply plug in the limiting value that you're given for x. So in this example, we're looking at what happens as x is approaching 2. So the limit of our numerator can be found by simply plugging in 2 for x. And the limit in our denominator is the limit of a polynomial, so we can evaluate it by just plugging in our limiting value for x. So let's see what we're left with here. In our numerator, we have 2 times 2 cubed, which is 8, minus 1. And then divided by 3 times 2 squared is 4, plus 4 times 2 is 8. So in our numerator, we have 16 minus 1, or 15, divided by 12 plus 8 is 20, and this simplifies to 3/4 if we divide top and bottom through by 5. So here we have a limiting value of 3/4, and now notice for this limit of a rational function, instead of making use of the quotient property, and what we've already figured out about polynomials, we get the exact value for our limit by making use of these properties as what we would have gotten from simply plugging in the value of x equals 2 to our function. So here, because a rational function is just a quotient of polynomials, by using the quotient rule or the quotient property, and the fact that the limit of a polynomial is just the value of the polynomial at that point, we have the following second half to our theorem involving the limit of a rational function. So here's what it says. if f is a rational function, that is the quotient of two polynomials, and a is some real number, such that f of a is defined, that is, our denominator is non-zero, then the limit of that rational function is just the value of the function at x equals a. So here we see that for polynomials or rational functions, which are quotients of polynomials, the limit is just the value of the function at x equals a, whatever number we're approaching. Okay. So using that result, let's look at the following example. We're asked to evaluate the given limits, and in part A, we have the limit as x approaches -1 of a polynomial. So using the theorem that we just established, we can say, well, since this function is a polynomial, we can evaluate by just plugging in the value of x, which was -1, for our function. So here we have 2 times -1 cubed would be -2, minus -1 squared is 1, so we're subtracting 1 there. Minus 6 times -1 gives us +6, and then +1. So here, plus minus 1 terms cancel. We're left with -2 plus 6 is 4. So this, of course, in part A is much easier than making use of our limit laws to split that up into each individual piece. We can simply plug in the value for x now. Now in part B, we have the limit as x approaches -2 of a rational function, the quotient of two polynomials. So using our new theorem, we know that we can evaluate this by simply plugging in the value of x to our function, as long as the function is defined there. So let's see what we have. For our numerator, we're going to have -2 plus 6 divided by 8 times x, which was approaching -2, minus 5. So we're left with 4 divided by, let's see, we've got -16 minus 5, so -21, or -4 over 21. All right, so certainly in part A and B, this is much easier than making use of each of those limit laws. So in part C, we have the limit as x approaches 2 of the square root of this polynomial function. So recall here that we can rewrite the square root of a function as that function, in this case 3x squared plus 2x, raised to the 1/2 power. So recall from your pre-calculus courses that the square root of some quantity x is the same as x to the 1/2 power. So here, if we're taking the square root of a function, I could first rewrite it as that function being raised to the 1/2 power. And what this allows me to do is make use of the power property for limits. Namely, the limit of a function being raised to a power is the same as first taking the limit of the function, 3x squared plus 2x, and then raising that value to the 1/2 power. Now, inside of our brackets here, we're working with the limit of a polynomial function, and as we did in part A, to evaluate the limit of a polynomial, we can simply plug in the given value for x. So here we're going to have 3 times 2 squared plus 2 times 2, all being raised to the 1/2 power. So that leaves us with 12 plus 4 is 16 raised to the 1/2, or in other words, the square root of 16, which is 4. All right. So in part C, we see now if we're taking some polynomial raised to a power, well, because of the power rule and what we already know about polynomials, we can simply take the limiting value for x and plug it directly into our function. All right. So what we're seeing here is for most functions, as long as they're, well, I shouldn't say most functions, but for a lot of nice functions like polynomials, quotients of polynomials, or polynomials being raised to powers, we can evaluate the limit by simply plugging in the value of x. So let's look at some examples where that may not work out very well and what we would need to do to handle those cases. So in this next example, we're asked to find the given limit, and in part A, we have the limit as x approaches 4 of x squared minus 16 over x minus 4, which is a rational function. So whenever we're evaluating limits, usually the first thing that we would try to do is simply plug in the value of x that we're given. So here we would have 4 squared minus 16 over 4 minus 4, which gives us 0 divided by 0. So this is a limit which is said to be of indeterminate form. We'll talk more about limits of indeterminate form throughout the course. But the problem that we run into here is that our denominator, x minus 4, is undefined, or it's equal to 0 at the value x equals 4. So we can't make use of the quotient property for limits. Remember, the quotient property said, well, the limit of a quotient is the quotient of the limits as long as the limit of the denominator is non-zero. So if the limit of your denominator is 0, then we can't use that property. We have to think of something else here. So the way that we can handle this sort of indeterminate form is by trying to first simplify our function. So let's look at what we could do here. So we had the limit as x is approaching 4. And in order to simplify this function, we could try factoring the numerator. In this example, our numerator is x squared minus 16, which factors as x plus 4 times x minus 4. And then we're dividing by x minus 4. So after factoring, we see that there is one term in the numerator and denominator which is identical, namely x minus 4. And as long as x is not equal to 4, that is, as long as that factor is non-zero, I could cancel that factor on top and bottom. Now, why am I guaranteed that x would not be equal to 4 in this example? Well, we're taking a limit as x is approaching 4. Remember, the definition of a limit is that we're taking values of x that are very close to 4, but not equal to it. So since those factors of x minus 4 are non-zero, I can cancel them on top and bottom, and I'm left with the limit as x approaches 4 of x plus 4, which is simply the limit of a polynomial. And to evaluate the limit of a polynomial, we just plug in the indicated value for x. So here, plugging in x equals 4, we're left with a value of 8 for our limit. So in this example, part A, we had a function where if we just plug in the value of x, we got something that was undefined, something of the form 0 over 0, which we mentioned is called an indeterminate form for a limit. So we couldn't evaluate by simply plugging in. We had to try something else. And in part A, we saw that if we were to factor the numerator, we can cancel a factor of x minus 4, and we're left with the limit of a polynomial, which we know how to evaluate. So let's look at part B. We have the limit as x approaches -2 of a rational function, quotient of polynomials. So the first thing that we always try for limits is to evaluate the function at the given value of x. So here, if we plug in -2 for our function, we would have a numerator of 4 minus 6 plus 2, and our denominator is 4 minus the -2 becomes a plus 2 minus 6. So here, again, we have something of the form 0 divided by 0, which is indeterminate. Here our function is undefined at x equals -2, since we have division by 0. So if we use the same approach that we did in part A, we could try factoring the polynomial in the numerator and denominator. And in this example, our numerator can be factored as x plus 1 times x plus 2, and our denominator can be factored as x minus 3 times x plus 2. So in this example, again, we see that there is a common factor of x plus 2 in the numerator and denominator, and as long as that factor is non-zero, so as long as x is not equal to -2, which we know it's not since we're taking a limit as we approach -2, we can cancel this factor on top and bottom, and we're left with the limit as x approaches -2 of x plus 1 over x minus 3, which is now the limit of a rational function. So from here, we could evaluate by plugging in the value of x directly, and we have a numerator of -1 divided by -5. So canceling a negative on top and bottom, we're left with a 1/5 for the limit. So again, in part B, we see that if we have a limit of indeterminate form, we might try factoring the numerator and denominator and seeing if any terms will cancel to allow us to then take the limit. So in part C, we have the limit as x approaches 3 of 1 over x minus 1/3 divided by x minus 3. So here we see if we were to plug in x equals 3, our numerator is 1/3 minus 1/3, and then we're dividing by 3 minus 3. So again, we have something which is indeterminate of the form 0 over 0. So we can't evaluate by simply plugging in the given value of x. We could try the same process that we had previously in parts A and B, but we see that here our numerator and denominator have already been completely factored. So let's think about what else we could do here. So there's a couple of ways we could go about finding this limit. One approach would be to take the expression that we have in our numerator, 1 over x minus 1/3, and write it as a single fraction. So getting a common denominator for those two fractions, we could think about this as 3 over 3x minus x over 3x. So here we would get a common denominator of 3 times x. So 1 over x would then be equivalent to 3 over 3x, and 1/3 is x minus 3x, or x over 3x. Then the whole thing is being divided by x minus 3. So what does this allow me to do? Well, in our numerator, we can subtract these two fractions, and we have 3 minus x over 3x, which is then being divided by x minus 3. So what I don't like here is the compound fraction. That is a fraction within a fraction. So to rewrite this, or to eliminate that compound fraction, I could multiply my fraction through by 3x over 3x. So here I'm just multiplying by 1. I'm not changing the value of my function. But that then simplifies my numerator, because the division by 3x will then cancel with this 3x that we multiplied by. And we are left with the limit as x approaches 3 of 3 minus x over x minus 3 times 3x. So at first glance, it seems like maybe this doesn't simplify nicely, but we'll notice that if we were to factor out a negative from the numerator, I would have a x minus 3 times negative 1 for my numerator, and we're dividing by x minus 3 times 3x. So at this stage, we find there's a common factor of x minus 3 in the numerator and denominator, which we can cancel since we're only taking values of x that are close to 3. And we're left with the limit as x approaches 3 of negative 1 divided by 3x. So now this is the limit of a rational function, and I can evaluate by simply plugging in the value for x, which would give me a negative 1/9. All right. So in these examples, we see that if initially plugging in the value of x gives you a limit which is of indeterminate form, we might have to manipulate the function by, say, factoring it, or combining some like terms in order to get something which cancels and then can be evaluated using our earlier methods. Now in our next example, we'll have something similar to illustrate another technique which we could use to evaluate indeterminate limits. So in this next example, we're asked to find the given limit. And in part A, we have the limit as x approaches 36 of the square root of x minus 6 over x minus 36. So as always, the first thing that we would try to evaluate any limit is plugging in the given value of x. So here we would have the square root of 36 minus 6 over 36 minus 36, which reduces to 0 over 0. Again, this is an indeterminate form. So we can't evaluate the limit directly in this way. So if we try to use the same approach that we used in the last example, we might try to factor the expression which appears in our numerator and denominator. But notice that these expressions have already been completely factored. Now, technically, we can factor our denominator if we're a little bit clever, and we'll take a look at that in just a moment. But another approach which we can use here is to rationalize the numerator or the denominator. So the expression that we have in the numerator, the square root of x minus 6, we can rationalize by multiplying by what's called its conjugate. So let's take a look at this. Our function was the following, and the expression that I have in the numerator, square root of x minus 6, I could multiply by its conjugate, which would be the expression square root of x plus 6. Now, if I multiply my numerator by that term, I must also multiply the denominator by that same term. Now let's see what that buys us. So in the numerator, if we multiply out these terms, we have the square root of x times the square root of x, which would be x to the first power. Then multiplying my outer two terms, I would have the square root of x times 6, so I have 6 root x. But then when we multiply the inner two terms, negative 6 times the square root of x, well, I then am subtracting 6 times root x, so that cancels with the positive 6 root x we had for the outer terms. And then multiplying my last two terms, we have a negative 6 times positive 6, which is minus 36. And then we're dividing by, well, we had a x minus 36, which we were then multiplying by the square root of x plus 6. So at this stage, we see that there is a common factor of x minus 36 on top and bottom, which we can cancel out since x is only approaching 36. And we're left with the limit as x approaches 36 of 1 over the square root of x plus 6. So after we've simplified our function, we can now evaluate by plugging in the given value of x. So we would have 1 over the square root of 36, which is 6, plus 6, and we're left with 1/12. So this method, which we illustrated here, in this first step, where we multiplied our numerator and denominator by the square root of x plus 6, this is called rationalization of the numerator. So here we were eliminating the square root term that appeared in our numerator, and we saw that we were able to simplify our function nicely. Now I mentioned that we could have also seen this by factoring. So if we're a little bit clever, the original function that we're given, we might recognize that the denominator, which was x minus 36, could be factored as a product of square root of x plus 6 times the square root of x minus 6. You can see if you expand that denominator, it's exactly x minus 36. And from here, you could cancel the square root of x minus 6 factor, and you get exactly the same expression that we had below. 1 over the square root of x plus 6, which leaves us with 1/12. So if you recognize that that denominator factors, you could also use this approach. So in part B, we have a similar problem. The limit as x approaches 9 of x minus 9 over the square root of x minus 3. So if we plug in 9 for x, we again have an indeterminate limit of the form 0 over 0. So there's a couple of ways we could go about handling this limit. One way is by factoring. Similar to what we saw in part A, we might recognize that our numerator, x minus 9, can be factored as the square root of x plus 3 times the square root of x minus 3. And then we're dividing by the square root of x minus 3. So this allows us to cancel a factor of root x minus 3 on top and bottom, and we're left with the limit as x approaches 9 of root x plus 3. So plugging in 9 for x, we have the square root of 9, which is 3 plus 3, So we're left with 6 for our limiting value. Now another approach which we could use here would be rationalization of our denominator. So if we had the limit as x is approaching 9 of x minus 9 over the square root of x minus 3, well, I could multiply my denominator by the square root of x plus 3. And if I multiply the denominator by that factor, I must also multiply the numerator by that same expression. So doing this, we have the limit as x approaches 9 of x minus 9 times the square root of x plus 3, and expanding the product of square root of x minus 3 and square root of x plus 3 in our denominator, we're left with x minus 9. So we then see that we can cancel the common factor of x minus 9 in the numerator and denominator, and we're left with the limit as x approaches 9 of the square root of x plus 3. And by plugging in x equals 9, we have 3 plus 3, or 6, for the limit. So we get the same value using either approach there, that rationalization or by factoring. So in this first part of our section, we've been discussing how to evaluate the limits of different functions by making use of the limit properties, or by some algebraic manipulation and then using the limit properties. But we haven't considered the question about whether a limit is always defined or whether a limit will always exist. So in the last part of our section, we'll talk a little bit about existence of limits. So there are some functions or some limits where it is possible that the limit of that function, say f of x as x approaches a, does not exist. So in particular, if there is no number, capital L, which the values of our function are approaching as x approaches a. So to illustrate where some limits may not exist, let's look at the following examples. So in part A, we're asked to evaluate the limit as x approaches 0 of 1 over x. So typically the first thing that we would try for a limit is to plug in the given value, which would give us 1 over 0, which is undefined here. Recall, division by 0 is undefined. So we can't simply evaluate our function at the indicated value of x using the quotient rule for limits because the limit of our denominator is 0. So another way which we could try to proceed is by simplifying our function, seeing if any common factors cancel. But the function 1 over x is already in simplified form. We can't manipulate it in any way such that something would cancel. So another approach we could use is the same approach that we used in our first example. Let us consider a table of values. So that is values of x and our function f of x, which is 1 over x. And we want to choose values of x that are close to 0, but not equal to 0. So we know that for x equals 0, our function is undefined. Now let's say that we're moving closer to 0, but not equal to 0, maybe taking 0.1 or 1/10. So our function f of x, 1 divided by 1/10, would give us a value of 10. Now if we move a little closer to 0, let's say we take 0.01 or 1/100th, Well, our function, 1 divided by 1/100th, is 100. Or if we move even closer to 0, let's say 0.001, 1/1000th, well, our function, 1 divided by 1/1000th, gives us 1,000 for the value. So we're seeing here that as we're moving closer to 0, the values of our function seem to be getting larger. Now let's say that we were working with values of x that are negative but close to 0, maybe -1/10. So -1/110 gives us -10 for the value of our function. If we move a little closer to 0, say -0.01, the value of our function is -100. Or if we take -1,000th, the value of our function is -1,000. So here, by looking at the values of our function 1 over x, as x is approaching 0, we see the values are not approaching any number. They're just getting larger and larger and positive or negative valued. So since there is no number which we're approaching as x approaches 0, we would say that this limit does not exist. Now we could have also seen this by examining the graph of this function. So if we consider in the xy plane the graph of 1 over x, we have the following function. And we can see that as we're closing in on x equals 0, the corresponding values for our function, as we saw in the table, are either becoming infinitely large in the positive direction or are becoming infinitely large in the negative direction. So since there is no number which we're approaching, this limit does not exist. So you'll typically see limits which do not exist if, when you evaluate the function at the indicated number, you have division by 0. That is, if you have some non-zero number, in this case 1, divided by 0, we'll see these functions which do not have limiting values. So in part B, we have something similar. We've got the limit as x approaches 1 of x squared plus 1 divided by x minus 1. So if we plug in the given value of x, we would have 2 divided by 0, which is undefined. And again, we would see that this limit does not exist since we have something of the form a non-zero number divided by 0. So let's justify why this limit may not exist. So if we were to think about this in the following way, we could think about the limit of our quotient as the limit of a product of two terms, let's say x squared plus 1 times 1 over x minus 1. So my numerator I could factor out as an x squared plus 1, and then the limit, or the product property for limits, says I could take the limit as x approaches 1 of x squared plus 1 and multiply by the limit as x approaches 1 of 1 over x minus 1. So the limit of this first term is 2, simply the limit of a polynomial, and I claim that this second factor is the factor which makes this limit not exist. So if we consider a table of values for that function, let's say x and 1 over x minus 1. Well, as we get close to 1, let's say if we're taking 1.1, then the value of our function is the same as 1 over 1/10, or 10. If we move a little closer to 1, let's say 1.01, the value of our function is 100. Or 1.001 gives us a value of 1,000. We know when x is equal to 1, the function is undefined, and if we take values that are a little bit less than 1, like let's say 0.9, we have -1 or -10 for the value of our function. If we move a little closer to 1, say 0.99, we have -100 for the value of our function. So again, we're seeing that this second term does not exist. Therefore, the limit itself does not exist. All right. So in our last couple of examples, let's consider piecewise defined functions where a limit may not exist. So in this first example, we are asked to consider the function f defined as -1 if x is less than 0, and +1 if x is greater than or equal to 0. And we're asked to find the limit as x approaches 0 if it exists. So there's a couple of ways that we could go about evaluating this. One would be to consider a table of values. So we want to consider values that are close to 0 but not equal to 0. So let's center our values around 0. And let's start by taking values of x which are a little greater than 0. So we know at x equals 0, our function would be valued as 1, since when x is equal to 0, f of x is defined as 1. And for any value of x that I take which is positive, so let's say that we're taking 0.01, something that's close to 0 but not equal to it. Well, since that value of x is positive, f of x is defined as 1. If we move a little further out, say 0.1, we still have a value of 1. Now, if we move a little bit to the left of 0, let's say we take -0.01. Well, since this value of x is negative, the value of our function is -1. Or if we move a little farther out, say -0.1, the value of our function is still -1. So what we're finding here is as the values of x are moving towards 0, but are less than 0, we have a value of our function which is -1. So we might think that that's our limiting value. But if we take values of x which are positive, and we're starting to close in on 0, we see the value of our function f of x is always equal to 1. So there is no single number which we're approaching as we approach 0 from both directions. If we approach from one side, we have a value of -1. As we approach from the other side, we've got a value of +1. So there is no single number which is being approached. So we would say in this case that our limit as x approaches 0 of this f of x does not exist. Now we could have also seen that from the graph of our function. So in the xy plane, if we graph our function, well, for all values of x which are greater than or equal to 0, the value of our function is a positive 1. Whereas for all values of x that are less than 0, we have a value of our function of negative 1. So for our limit, as x is approaching 0, there is no single y value that we're approaching on the y-axis. We see that there's a jump in the value of our function, so there's no single number which we're getting close to. So let's consider something similar. In the next example, we have the function f defined as x squared if x is less than negative 1, x plus 2 if x is between negative 1 and positive 1, and 3 minus x if x is greater than or equal to 1. So we want to sketch the graph of that function and then use the graph to find the limits of the function as x approaches negative 1 or positive 1 if they exist. So let's see if we can sketch the graph of this function. So in the xy plane, we have a function which is first defined as x squared if x is to the left of negative 1. Let's see what happens when x is equal to negative 1. Or as we're getting closer to negative 1, we have a graph which looks like the graph of x squared. So at x equals negative 1, it would have a value of positive 1, and it's a parabola that is opening upward. So it looks something like this on that first segment of our domain where x is less than negative 1. Now, since we have a strict inequality there, x is strictly less than negative 1, at x equals negative 1, I'm going to leave a hole in the graph for now. Now, as we move to the next part of our domain, where x is equal to negative 1, our function is defined as x plus 2. So at x equals negative 1, we would have a y value of 1. So we can close off that point at negative 1, positive 1. And the graph of the function x plus 2 would be a line of slope 1 and y-intercept positive 2. So we have a line which is increasing, and as we are approaching x equals 1, well, this was a strict inequality, so we're approaching a value of 3, a y value of 3. So if I extend my y-axis here, we've got the following, and I would leave a open point at that value where x is equal to 1, since this was a strict inequality. And for the last part of our function, we have 3 minus x if x is greater than or equal to 1. So when x is equal to 1, we would have a y value of 2. So at the point 1, 2, I'm going to have a closed point. And then the graph of 3 minus x is a line of slope negative 1. So from here, our graph would look like the following. So given this graph, we want to find the limit as x is approaching negative 1 of our function. So looking at our functional values, as x is closing in on negative 1, we see the values of our function are approaching this y value of positive 1. Now for the limit as x approaches positive 1 of f of x, let's see what we have. So as our x values are approaching positive 1, we see, well, as we're closing in on 1 from the left-hand side, the values of our function are approaching 3, And as we're closing in on 1 from the right-hand side, we have values of our function that seem to be approaching 2. So since there is no single number which we are approaching, we would say that this limit does not exist. All right, so this example illustrating that for a piecewise function, the limit may or may not exist at a given value, depending on whether the function makes a jump at that value of x. So in our last example, we're considering an application of these limits. So here we're told that there is an independent driver working for a New York City taxi company that pays for the cost of fuel and a maximum of $115 to lease a vehicle and a taxi medallion for a 12-hour shift. So the driver's cost for working that shift is approximated by the following cost function, c of x, which is 115 as the fixed cost for the lease, and then a variable cost of 0.2, so $0.2 or 20 cents for the cost of this medallion, where x is the number of miles driven. So in part A, we're asked to find the average cost per mile, that is c bar of x. So recall that the average cost, c bar of x, is found by taking the cost function c of x and dividing by x. So we have 115 plus 0.2x all over x, which can be simplified as 115 divided by x plus 0.2. So this would be our average cost per mile. Now in part B, we're asked to find and interpret c bar of 50. So here c bar of 50 would be 115 over 50 plus 0.2. So let's see what we're left with here. So dividing top and bottom through by 5, we would have 23 over 10 plus 0.2. So that gives us 2.3 plus 0.2, or 2.5. And this would be the average cost, so dollars per mile driven. So the interpretation of this value would be if the driver drives a total of 50 miles, the average cost for them per mile would be $2.5 per mile. So let's consider another one. Here we are asked for c bar of 230. For the ease of numbers, let's maybe make this 250. So we would have 115 divided by 250 plus our 0.2. So let's see what we're left with. Dividing top and bottom through by 5, we would have 23 over 50 plus 0.2. So we could write that as 46 over 100 plus 0.2, which gives us 0.46 plus 0.2, or $0.66 per mile for our average cost. So the interpretation here is if the driver drives a total of 250 miles, the average cost to him is $0.66 or 66 cents per mile. So by driving a farther total distance, it decreases his average cost per mile. We could then ask the part D question, well, what about the limit as x approaches 250 of c bar of x? So taking the limit as x approaches 250 of our average cost function, which was 115 over x plus 0.2. Well, the first thing that we try to do for any limit is plug in the indicated value of x. So we would have 115 over 250 plus 0.2, which gives us, as we saw in part C, a value of $0.66 per mile. So this limiting value would mean that as the number of miles that the driver has driven is approaching 250, his average cost is approaching $0.66 or 66 cents